This is the first in the series of video lectures on code optimization. For this first set of video lectures in this topic, we're going to look at register allocation. Register allocation is the problem of using the registers that are available in most CPUs and using those registers instead of the unlimited locations that we've been allowed to use in the intermediate representation. So for example, when you use LLVM, you can assign things to as many temporary locations as you want, like there's no limit. So when you start assigning things to T1, T2, you can have T1000 if you want. It doesn't stop you from creating as many of these locations as you need when you're doing the code generation. But when it comes to the actual hardware, there's all of these locations have to be stored somewhere. So we're assuming that they are all stored somewhere in RAM, in your main memory, that there is a location here for T1, for example. And then when the CPU, which is the way over here, wants to use it, it's going to grab this. It's going to go through. Typically, there are some intermediate steps along the way, like there is an L2 cache and an L1 cache. And then finally in here, there will be a register R1, a register R2, etc. So when we want to actually execute a CPU instruction, we have to first collect T1. It might get stored in the L2 cache, and then it might get stored in the L1 cache, and then finally T1 might get loaded into register R1, and then we can use it. But this is, as you can see, an expensive operation. You might get lucky and you might find T1, the L1 cache, in which case it's somewhat faster, or in the L2 cache. But in order to actually compute anything in the CPU with that value, you have to get it into the CPU and store it in a register. So for the purposes of these video lectures on register allocation, I'm not going to make a distinction between L1 cache, L2 cache, and RAM. The main distinction I'm going to make is I want to be inside a register in the CPU, or I'm going to have to go and either store it somewhere out or load it from outside the CPU. Anything outside the CPU is going to be relatively more expensive. So we want to make sure that we use the registers as effectively as possible. So when we did intermediate code, by having unlimited temporaries, it simplified our code generation, and it also simplifies code optimization a great deal. But it does complicate the final translation to assembly language, because at that point we have to deal with register allocation as a problem. And it's the right place to have it. So I think that's exactly why we have designed our intermediate representations in that way, is to make sure that we do the register allocation just as we are doing our translation into assembly language, because it's going to depend on what CPU you have. Certain CPUs might have 16 registers, some might have hundreds. And so it depends on the CPU architecture, how efficient can you make your code, and how can you convert these temporary variables into registers. Obviously, you cannot convert all 1,000 of these into registers, so you'll have to reuse them somehow. So RT1 might go to register R1, and so might a different temporary, and so might T1000, depending on where you are in the program, right? So we want to reuse these registers as much as possible for different temporary variables, or any location really that we have in the intermediate representation. So the problem of register allocation is to rewrite the intermediate code or map it and use sort of these locations and map them into machine registers. And we have a limited number of machine registers, definitely a lot less than the number of locations that we generate in intermediate code. So the method we want is to assign multiple temporaries to each register, and we have to make sure that we don't change the program behavior. Like we can't, for the purposes of making things efficient, we cannot introduce any potential errors into the code. So let's take an example. Let's see these set of 3 assignment instructions. So you have a equals c plus d, e equals a plus b, and f equals e minus 1. Let's assume that a and e are not used anywhere else later on in the code. So for some reason we are assigning something to a, but we're never using it. We assign something to e, but then we use it right away in this statement. If this assumption is true, that a and e are never going to be used, reuse these dead temporary locations. So it's dead means it's never used. And if it's never used, we can take that location for a and e and reuse it when we are doing register allocation. So we can allocate A, E, and F. All of them can be assigned to one register R1. So A is stored in register R1, and then it's used in this, right? Just like here. R1 is used, and then we're adding it to R4. R4 is somewhere the value of B is stored. And then E is also assigned to R1, right? So this E is also assigned to R1, and it's used right away. And as soon as we use it, we know that E is dead. It's not used anywhere else. So we can clobber the value of E. So E goes away, and we are storing F in the location of register R1. What we want is some automatic method that does this kind of reasoning, right? It says, these values are not going to be used, therefore I should reuse that register and use it for something to store something else. So that's a kind of algorithm we want. So register allocation is really as old as compilers. The first compilers had to deal with register allocation. There was one of the initial problems that was handled in the original Fortran compilers in the 50s. It was a very crude algorithm at that time. The main breakthrough came in the early 80s, where people reduced the problem of register allocation to the problem of graph coloring, which was being increasingly studied algorithmically at the time. This reduction of register allocation to a well-known problem led to many efficient algorithms and also an understanding of why register allocation is difficult. And we'll look at why register allocation can be reduced to graph coloring in a few slides later. But that really was a breakthrough in terms of understanding register allocation. As a result, many heuristic algorithms were developed that had reasonably good performance in practice. And so it was simple, it works well in practice, and it works not just for small windows of code, but you could analyze sort of large chunks of code of your control flow graph in order to do register allocation more efficiently and more optimally. So the principles of register allocation are as follows. So two temporary locations, T1 and T2, can share the same register. And a temporary here can be either a real temporary, which was introduced when we did code generation, or it could be just a location, like a local variable that needs to be stored somewhere and used. So temporaries here stand for both of those things, any location really. And you can share the same register for any two locations if at most one of them is live, right? So live means that it is going to be used later. So live means not dead. As we saw, dead means it's not used anymore. So live, in the opposite of dead, here means that it is going to be used. Only one of them is going to be used. So T1 might be used later, or T2 is used later. If T1 is used later, I can get rid of T2 and store T1 in the register, and vice versa. And if T1 and T2 are alive at the same time, then they cannot share a register, because they can both we need both of these values to be alive, and because they can be used in the program later on. They cannot share the same resource, the same register. So what we need is some kind of liveness analysis, like which locations are live at the same time. So there might be various local constraints on your program, in each basic block, you might see that some locations are going to be more long-lived than others, and we need to analyze this over the course of the entire control flow graph. So let's look at a control flow graph here, an example one. And what we want to do is compute the live variables at each point in this control flow graph. So if I start at the bottom at the exit point. So this here is the exit point of the program, and I ask the question of what value should be alive at that point. Well, what I want is the value of b, because b is being computed here and it's passed down. Essentially, we are assuming we are returning the value of b from this program. And so I need to make sure that I keep that value of b when I exit the program. So let's go back one step and see what is needed for computing b. Well, you need f and you need c. You need to have f and c, and we need that from the previous basic block. So there's two possible routes that are coming in here to this basic block. One from f equals 2 times e, and then the other one from these two, which define variables b and e here. So in this case, you should get f and c from either branch, right? Either the left or the right branch. And let's go to the left branch and see, well, what is needed to be coming into that. This is using e. But notice that it's defining the value of f. So if I need c, right? So I need to have c. I need e because I'm using e. I should need f, but I don't need to have it coming in because I'm defining it in this basic block, right? So f is not needed as part of this input to that basic block because f is being redefined inside that basic block. If you look at this point in the program, we know we want a b because I've just computed it. So this b has to be in there. We need an e, so that's why we need e there. And finally, we need an f and c, so f and c has to be in there. And so what's coming into this basic block has to be, so notice that we're defining b, so we don't need b coming into this block because we're defining it. We do need e, so we need f and c because we need it for this. And we need d because d is used as part of the input to computing b in that statement. So d is required as well. It has to be coming from the previous basic block or as the input to this function or program. So this control flow graph could be, the control flow graph for a function or some part of a larger function. Now let's look at what's needed before each statement here. So this is e equals d and f. So we need d and f. We also need c because we need c going out here. So f and c are needed. We need d because we are computing it. We need f another way because it's using f in here as well. Now if you go one step higher, we need an a because it's being used, and we need an f and a c because we need it to be part of f and c here. We don't need f here because f is being defined as you saw before. So we need a because it's used. We need f and c because we need to keep those values around. It's going to be used later. In fact, it's going to be used here, right? That's why we need to keep it around. And when we come back into this loop, we need a b and a c. And we want to make sure that we carry this f back so that f is always defined. And notice that c is also needed to be carried forward because we can have, so it's c and f, but we're also using b and c. So c, you need it two different ways. You need it for carrying forward f and c, but you need b and c because they're used in the right R value of this assignment. Now that we have all of the requirements of which variable is alive at which point in this control flow graph, we can now look for the dependencies between these variables, between these locations. So we can draw this as a graph where every node here represents this relationship that's represented here. So F and C have to be alive together. So you can see that there is an edge between F and C here. Going here, there has to be an edge between B and E because B and E coexist. There has to be a node between B and F because B and F exist in this set. There has to be a node between E and C because these two exist, and then F and E because these two exist in this set. So if I was, and of course B and C as well because those two are in the same set. Now if you look at each one of these, so like A, F, and C, AF and F and C are together, A and C are together, right? So, and so on. So every single one of these can be represented in a graph, and the graph consists of these edges. These edges represent the dependencies that we've computed here doing this live variable analysis. And now if you look at this graph, you can see it's pretty obvious what the connection to graph coloring is, because if I have an edge between A and C, that means that A is connected to C via an edge. And if you imagine that the number of registers, each register is assigned some color, then two nodes that are connected by an edge cannot have the same color, right? So think of the registers as having colors instead of names. The blue register cannot be assigned to both A and C because they're connected via an edge. So A and C have to be in different color registers. So it's a straightforward way of reducing register allocation into graph coloring. So this graph is called the register interference graph. We construct this undirected graph. It has a node for each location or each temporary variable, and an edge between T1 and T2 exists if they're alive simultaneously at some point in the program using this liveness analysis that we just did. So if two nodes here, each node is a location or a temporary, has an edge, then they cannot be allocated to the same register. So in this example, A and C cannot be in the same register, but A and D, which don't have an edge, A and D doesn't have an edge between them, they could be in the same register and it's fine. So the register interference graph extracts exactly the information we need to characterize what is the legal register allocation, and it gives a global view over the entire control flow graph of the register requirement. After we construct the register interference graph, the register allocation algorithm is in fact architecture independent. It doesn't really depend on a particular CPU. All you need to say is how many registers are available, and the register allocation algorithm can now do the allocation in a fairly abstract way, abstracted away from CPU specifics. Graph coloring, as you probably have seen before, is an assignment of colors to nodes such that the nodes connected by an edge have to have different colors. They cannot share a color. And this is related to things like coloring on a map so that adjacent countries don't get the same color, etc. And graph coloring is a useful algorithm that covers lots and lots of use cases, and register allocation is just one of them. If we assign colors to these nodes, each color represents a register, then a graph is k-colorable if it has a coloring with k colors. So in this case, we can assign 3 different colors to each of these nodes, and so this particular graph has a valid assignment because every edge, you can see that every edge you have different colors between every edge. Now in our problem, colors equals registers, and we need to assign these colors, aka registers, to graph nodes, aka locations or temporaries. So I'm going to use locations and temporaries interchangeably in these slides. I have K is the number of machine registers. Then if I construct a register interference graph, and that graph is K colorable, then there has to be a register assignment that uses no more than k registers, right? So as long as you can assign k colors to the graph, then we just take each color and assign it to one of the registers in the CPU. We are done with our register allocation task. So let's take this example that we saw before, and it turns out that it is 4 colorable. So if you have 4 registers, you can assign a register to each node in this graph. Each one is going to be using that register and sharing that register sometimes with other nodes because they are not alive at the same time. So for example, E is assigned to R2 and A is assigned to R2 as well. But since E and A don't have an edge connecting them, that means they're not alive at the same time. So we can reuse that register. On the other hand, if a node is connected, so this F is connected to D, then it's connected via an edge, then the registers that they use should be different because they can't reuse the same register. So in this graph, it turns out it's possible to do a 4 coloring, and therefore we can assign 4 registers to every node in this graph, and we are able to use the registers as efficiently as we can. Let's take this example we saw before again, and we compute giving it. So now we have A, B, C, D, E, and F as these locations. Then what we can do is take this assignment of A to R2, F to R1, etc., and replace every variable here with a register. And then you can see that even though we have a large number of temporaries or locations, A, B, C, D, E, F, we can get away with exactly 4 registers in order to compute everything we need to do in registers only, just by constructing the register interference graph and then coloring it with 4 colors, aka registers. So the question is, how can we compute the graph coloring efficiently? Because it's a hard problem. For small numbers, especially, it can be pretty hard. For large numbers of colors, it becomes easier. It's still an active area of research in theory in terms of graph coloring. So lots and lots of theoretical research has been done on graph coloring, and all of it can be applicable to register allocation. So it's not an easy problem. The problem is NP hard. There are no efficient algorithms, and the solution that is used is to use good heuristics to solve this NP hard problem. So problem is NP hard if it's as hard as any NP complete problem, and it has to compute an actual value, not just a yes/no answer. It's going to be hard to find an algorithm that isn't exponential time for this problem. So what we're going to do is use some heuristics. Sometimes you can use greedy algorithms that are suboptimal in order to get a solution to the graph coloring, aka register allocation problem. A coloring actually might not exist for a given number of registers, in which case we will look in the next video lecture of how we can spill a register to memory, which will allow us to use the rest of the registers as efficiently as possible while still compiling this program to use memory when needed. So certain locations will be loaded and stored from main memory or the cache, and others will keep in a register, so as many as we can. We'll look at register spilling in a later. So the main idea of solving whether a graph is k-colorable is, so this is one way to do it. This is not the only way to do it, but this is the algorithm we're going to study, is to pick a node with fewer than k neighbors. So it's crucial that it's fewer than k, because we want to assign each node to one of these k colors. So we'll pick a node with fewer than k neighbors. We'll remove n adjacent edges of this node T to create a new graph. So essentially, we create a new graph that is exactly the same graph, except it's missing this node T, and all of the edges of that node are removed. So it becomes a simpler graph. If this new graph is k-colorable, then so is G, because we picked a node with fewer than k neighbors. So if you add in that node, we should be able to use k colors to label. We should be able to pick a color for node T that isn't the same color as its neighbors, given that it has fewer than k neighbors. So by definition, this should work. And what we do then is, if C1 through Cn are the colors assigned to the neighbors of T, then since n is less than k, we pick some color for T that's different from its neighbors. So the heuristic for graph coloring is as follows. We would pick nodes and remove them, excise them from the graph, like extract them out, remove the edges, and put them in a stack. So pick a node with fewer than k neighbors, put it on a stack, and remove it from the register interference graph. Repeat until the graph is empty. And then we go through the nodes in the stack with the last node added. We pop that out. We pick a color different from those assigned to already colored neighbors. So when we start, the graph is empty and the stack is full. The first element we pop out of the stack, we can assign it to any color we want. And then we pop the next one, we assign it to a different color, etc., based on the edge relationships in the register interference graph. So let's look at this example of how this can be done. Let's assume that we have k equals 4. So we're looking for a 4 coloring of the graph, or in other words, we are looking to assign 4 registers to all the nodes in this graph. And the first step is we take a node with fewer than k, so fewer than 4 neighbors. Let's pick A and we remove it and push it into the stack. Then we choose another node. Let's choose D, take D out of the graph and push it onto the stack. As you can see, the graph gets simpler and simpler to color as we go further and remove each node. So let's check here that every node has fewer than 4 neighbors, so we're guaranteed to succeed the graph coloring at this point. So if you have a clique of more than 4, it might be impossible. So at least we know at this point that it's possible. So let's continue with the algorithm. Let's remove C, add it to the stack and remove it from the graph. Let's remove B, and now we remove E, and we're left with one node in the graph, F. We remove that one. And now we have a stack, which the top of the stack is F, and then we continue down the stack. And so the first thing we do is, now that we're done with the first part, we have the order of assigning colors to nodes. And we start coloring the nodes by starting from the top of the stack. So we pop F from the stack and we assign it to a register, R1, and I'll show them with different colors to make the comparison with graph coloring more apparent. And now we pop E. E shares an edge with F, so E must be in a different register from F, so we assign it a different register, R2. And then we pop B. B has edges with F and E, and F is R1, E is R2, so B has to be a different register from them, so R3. And then we add C. C is connected to E, F, and B, and we can see that E is R2, F is R1, and B is R3, so C has to be a different register, namely R4, the fourth register we are allowed to use. The next step is to pop the D. So this ordering ensures we can find a color for all the nodes, because we're doing it in this sequence. So now we pop out the D from the stack, and we can see that D is connected to E, F, and C, but it's not connected to B. So D and B can be in the same register. So D takes R3, which was previously used by B, right? So the structure of the program is such that we know that B is no longer required to be there when I use D. Their live ranges don't overlap. So D can be assigned into register R3 at this point. Then we take A, and that's the last node in the stack, and A is connected to F and C, so it gets a register R2 or R3. Either one can be chosen. So in summary, a register allocation is a must-have because intermediate code uses too many temporaries. And register allocation makes a huge difference in performance because you can do a lot of the computation without calling out to main memory, which is quite an expensive thing to do in modern architectures. And register allocation, as we saw, can be reduced to a graph coloring problem where the number of registers that we need to allocate are equal to the number of colors. So a 4-coloring problem on a graph, a register interference graph, becomes the solution to the problem of allocating each node, aka each location, to a register. So register allocation becomes equivalent to the graph coloring problem over the register interference graph.